Good morning, good afternoon, good evening, wherever you are. Tonight we have speakers from the United States, from Israel, from Canada, and from India. And we have listeners from all over the world. We'll soon ask you where you're from. And we're just waiting for a few more of you to join in before we officially start. So thank you all for being here. Thank you so much. But quantum computing is a bit of a riddle, in fact. I think many of us are not sure where we are. Is this actually happening, or are we not sure? And this is why we decided to start our program as EFI-Entrepreneurship Forum of Israel with this intriguing topic. And you're welcome to fill in the questionnaire. Where are you from? Well, I'm from Israel. I'm the chairperson for the Israel Entrepreneurship Forum, EFI, which we rebranded recently, formerly the MIT Enterprise Forum of Israel, that has been active since 1994, in fact. And EFI works both locally and globally. We actually have currently are working with companies in Japan and in Greece, and have done things all over the world, especially in the United States, in order to make lives easier for entrepreneurs, mainly entrepreneurs in high technology, and with a special focus on women and minorities. And this event is part of a series of events that we're going to hold in the next few years, which we named The Decade Ahead. And we're going to talk about green hydrogen and artificial general intelligence and lots of other extremely interesting topics that are going to change our lives in the next decade. Further information, please find on our site. And you're very welcome to all join us on email. Before we start, I'd like to thank our sponsors and partners. And our main supporting partner tonight is the US Embassy in Israel through their public diplomacy grant programs. So thank you very much. Special thanks to Ellen Schnitzer, who's the head of the public diplomacy grant program in Israel. And we have so many partners, excellent partners from all over the world. I'll start with the E-Forum, formerly the MIT Enterprise Forum Cambridge, and the MIT Enterprise Forum of Central and Eastern Europe, the MIT Enterprise Forum of Greece, and the Entrepreneurship Forum of Spain, Ventec in California, formerly Central Coast MIT Enterprise Forum, and the MIT Club of Phoenix. We also have Global Entrepreneurship Network Israel as a partner here, and the Israel Advanced Technology Industries Organization named YATI. And special thanks to our in-kind sponsors, our auditors, PwC Israel, and Amir Gleit, who runs the high-tech group, and our legal advisor, Advocate Jody Stein of Perkon, Tzedek Latzer, and Baratz. And here I'd like to hand it over to Armando Viteri, a great friend of the EFI Israel. Armando is a repeat entrepreneur. He's a partner in a AMRITA Technology Partners, a boutique private equity firm based on San Diego. He had been a serial entrepreneur for most of his career, but now focused on leading established companies within that portfolio, which includes Techniquesoft, Premier AI/ML consultancy, an implementation firm, as well as Neubloc, a premier embedded and Internet of Things development firm. 70% of the global cloud is driven by storage device code developed at Neubloc. Isn't this amazing? So thank you, Armando, my partner and member of our board management committee. Thank you for being so central in creating this series of meetings. And if I may hand it over to you, please take it from here.
Ayla, thank you. So this is a series of programs that originated over a glass of wine between Ayla and I, in which we talked about the idea of what technologies in the next 10 years are really going to be transformative in our individual lives. And certainly one of the very first ones that came to mind was what will be the ultimate impact of quantum computing. So we gathered together a group of speakers and panelists today that I think it's going to be a highly informative group. And we have an audience. As I was watching all the hellos flying through the screen, I counted off 6 continents that are participating here. I'm very disappointed in Antarctica. We're going to have to do better next time out of Antarctica next time. So let me go through and introduce these speakers. First of all, Brian Lenahan, who is the founder and chair of the Quantum Strategy Institute, a global nonprofit think tank devoted to the acceleration and adoption of quantum technologies. He's also the author of a best-selling book on Amazon, Quantum Boost, as well as 4 other books focused on the intersection of business and advanced technologies. Also on the panel and representing the Quantum Strategy Institute is AMRITA MANZARI. AMRITA has 8 years of experience in healthcare and the insurance industry as an IT professional. She's currently working as the architect for United Health Group and is head of AI and quantum machine learning at the Quantum Strategy Institute. Her career has been more of a transformation journey. She started her career journey as an automation engineer, but with passion to pursue research in the quantum field. She's now switched to becoming a quantum engineer. Also with us is Alex Keesling. Alex is not only a fraternity brother of mine from MIT, he's also, probably a bit more importantly, the CEO of QuEra Computing, which is a startup which spun out of a joint MIT-Harvard lab. QuEra is dedicated to developing a full quantum computing stack, leveraging some major new advances in quantum computing from both Harvard and MIT. Dr. Keesling is an inventor of the neutral atom quantum processor, which is used by QuEra, which was developed while he was getting his PhD at Harvard. Lastly, Nir Minerbi. Nir Minerbi is the co-founder and CEO of Classiq, an Israeli-based company developing a unique platform for quantum algorithm design. Mr. Minerbi has a history of leading cutting-edge technology teams and projects to extraordinary outcomes. He has a master's degree in physics and is a graduate of the prestigious Talpiot program, which has been described by Forbes magazine as being some combination of a Rhodes Scholarship, a presidential fellowship, and a Harvard MBA all rolled into one. The Classiq team is comprised of world-renowned scientists in quantum algorithms, quantum software development, CAD technologies, and more. Classiq recently raised a $10.5 million Series A round led by Teammate Capital and Wing Capital. So welcome, panelists. Let's move on to the agenda. Wrong way. There we go. Okay, so to kick this off, we've asked Brian to do a keynote presentation on how organizations should ready themselves for quantum computing. So with that, Brian, kick this off. Brian, you're muted.
And Armando, can you see my screen?
I can't see your screen. And there we are.
Good. Okay. Thank you very much. So let me just tell you a little bit about the Quantum Strategy Institute. As Armando suggested, it is a global think tank made up of quantum experts and enthusiasts from around the world. And our mission is devoted to the acceleration of the adoption of quantum technologies as a whole. Today, I'm going to be talking more about quantum computing, but generally speaking, our focus is on quantum technologies, including computing, sensing, and communication. We've brought together and been able to inspire people to join from senior roles in Google and McKinsey, in Quantinuum, Cold Quanta, and a number of other organizations in order to help bring quantum technologies to business. One of the things that I do with my own practice is I work with companies to help them determine or develop quantum roadmaps. And you have to be very cautious when you're developing quantum roadmaps with customers because you cannot simply focus on a hype around quantum computing or any other technology. It's important that they be able to understand how they can start to plan as well as invest in quantum going forward, either as a producer, researcher, consumer. So it's very important that we provide a balanced view in terms of what quantum computing can do. When I started getting involved in quantum computing about 5 years ago, it was a very different dynamic to where we are today, where we start to talk about tens and hundreds of qubits and the ability of quantum key distribution, the abilities of quantum random number generation, those things that are actually in market today. So it's important that we actually balance the view in terms of quantum computing. So that really speaks to the question of quantum readiness, and whether that's from the capabilities of production or the readiness of people to accept and use quantum with use cases. It's a very interesting question. You'll see on the right where the question is, which quantum trajectory will actually prevail? Is it going to be a very high, quick trajectory, or is it going to be much more moderated? You'll get opinions from people all over the map. The challenge, though, is the breakthroughs are happening very quickly. The use cases are being expanded. So it's very important that companies, whether you're scaling or you're corporate, start to think about what quantum could do for you. There will, of course, be certain use cases that some people will refer to as the killer app or the app that gets them involved in that activity. We'll talk about that during my presentation. So the 4 areas that I'd love to cover today are: what are the success tactics to prepare for the next generation of computing? What does hybrid mean in the quantum context? What level of knowledge do you as a business owner, as a IT professional need to know when it comes to making investment decisions around quantum? And how can those organizations prepare their teams? How can they find the talent, and how can they structure those external relationships? Let's start off with the first segment. One of the challenges that companies are constantly facing is that if they're looking to make any planning time, allocating resources, and allocating investment dollars, they need champions from the very top of the organization. if anybody here was involved in the artificial intelligence spectrum in the past number of years, the same thing was true. The question of bias, the question of black boxes, were there errors? Is there a bias that may impact your brand? So that for quantum, it's equally important to have champions who are at the top of the organization. Selecting priority use cases. It's easy to look at the existing media and decide that there are tons of possible use cases. But for each organization, it's so important that they need to start small, they pilot, they identify early successes, and then they broaden their relationship with quantum after that. I'll talk about some of those use cases on the next slide. The question is, will quantum solutions align? The whole definition of quantum computing versus classical computing, which is something I'll cover in a minute, it's very important. It should not just simply be the next shiny object that a company decides to invest in. You need to understand if the solutions align to those key business problems. The question around buy, build, or borrow is somewhat more defined in the quantum space in the sense that quantum is predominantly a cloud-based service with significant investments in the quantum computers themselves that are off-prem. So they are maybe in large server communities that are owned by the hardware manufacturer that will be licensed through software that is available through the cloud. So in that kind of environment, very few people are going to be building their own quantum computers, at least for the foreseeable future. And then thinking about a hybrid solution, I'll cover that in the next section, but essentially understanding what's the difference between classical and hybrid. So many CEOs that I talk to say, Brian, are you asking me to replace my full classical infrastructure? And that is not the case at all. We're thinking about areas where quantum computers are better suited or are the only things capable of attacking those business problems. And then the all-important quantum roadmap. Whenever I work with companies to help them understand what quantum could do for them, we start with their business problem. And then we do an opportunity assessment to understand if they are ready to accept or adopt quantum. And then we look at the use cases that they are most focused on, and then we start them on that 3-year roadmap. Any company should be thinking about quantum computing or sensing or communications in that same vein. What are some of those quantum use cases? Well, we've mentioned sensing, and we're talking about GPS, space navigation, capabilities where you're looking at penetrating the Earth, gaining new data. From a financial services perspective, a portfolio optimization. So how can you use quantum computing to better understand and optimize your portfolios? Similarly with traffic flow, whether that's consumer traffic flow or maybe your fleet delivery. From a communication perspective, today there exists a 2,000-kilometer quantum communication fiber-based system between Beijing and Shanghai. Similar in Chicago, implementing something on a smaller scale. Organizations like QuEra in the Netherlands are leading the charge around a quantum internet. So lots of use cases that are going on. You extend it to the data security. We'll talk about that as one of the next use cases, but what does that really mean? There's a little bit of text on this, but I want to make sure that you have a sense, and you're welcome to read it. But the question here is about something that cybersecurity experts call Q-Day. This is the day when the quantum computers will break the internet. So everyday transactions, security, privacy, identity, securing payments. How close can this use case of quantum be? You can see that in last year in Forbes, Arthur Herman described it as something that a classical computer would take 300 trillion years to crack the RSA 2048-bit encryption key. But a quantum computer can do that in just 10 seconds with those stable bits. Unfortunately, we don't have a computer today that has that many stable bits. But when will that happen? So the question for organizations and consumers is, when do you need to start thinking about security as it relates to quantum capabilities? Several media outlets have talked about, the question of harvest now and decrypt later, classical data that can be decrypted using quantum cryptography. And certainly a concern for many financial organizations is this question of, improving data, protect data patterns, understanding them, flagging potential fraud. As a former executive in a large North American financial institution, this was one of my areas of responsibility, and a quantum capability would have been incredible for us. What about stock valuation? Just a year ago, McKinsey and company had forecast how could it change their services, and they spoke to a specific instance, in this case, BBVA having a partnership with multiverse computing. This year, that partnership resulted in a 37 to 43% error reduction in their stock valuations by leveraging quantum capabilities. And it resulted also in now no increase in runtime or the number of runs. There are many examples that we need to think about in terms of quantum use cases. One other example I'll provide to you is this question that this example was provided by Janssen Pharmaceuticals. And it's very interesting because here is an opportunity to compare quantum computers with classical computers. You'll see the two columns that are labeled quantum, whether it's the 4 amino or 14 amino acid peptide versus the classical in those next two columns. They measure it by compute time, by energy, by the number of candidates they generate. And while you see some very different results, 1 second versus 870 seconds versus, in the classical case, 33,000 seconds. In the case of the 14 amino peptide, the compute time wasn't even completed due to the fact that it ran over a week in the FICO Express optimization. So there's no clear-cut solution. Quantum computers continue to get better, particularly in the biochemistry area. So it's important that you do that comparison between solutions. So what does that hybrid mean in the quantum context? Well, today over 95% of computing capability is classical. So it's going to be very difficult to replace all that. And do you really need to? You don't. There are lots of continuing reasons to use classical, let alone because of the investment. That infrastructure is in place. So then the question becomes, which problems should quantum computing address? Well, ideally, it's those that classical computers cannot. They are so complex, they are so hard that by definition, if it takes thousands or hundreds of years for a classical computer to be able to calculate that, then you look to quantum capabilities. Running comparisons like the one that I provided in terms of Janssen Pharmaceuticals, being able to understand how much energy it takes, what the compute time is, how many solutions that are generated as a result of this comparison. And then once you've done that, really understanding and designing systems that are seamlessly going to integrate. This is not as easy as it sounds in a one-sentence recommendation. So seamlessly integrating will be very important when you're moving data back and forth between classical and quantum systems. So what level of knowledge is really required to make those investment decisions? And this is a conversation that I have on a regular basis with business leaders, large corporates, small, people who are doing business development. At QSI, the role that is most interested in the message and the mission that we have today is business development. So organizations, which really represent about 99% of the activity in production and research, versus the 1% that exists today on the consumer side, you can imagine these business development folks are having a challenge reaching out to organizations to get them to buy. So the question really for them is, what's successful implementation? What's a successful tactic in the quantum world? So for C-suite and middle management, there's a very small percentage that are aware of or understand quantum opportunities. Ayla off the top, when people were joining, talked about it as a riddle. And quite often people will see it just as that. So not only do they not understand the quantum opportunities, they don't understand the technology. And anybody who is in business development who starts off with a conversation that discusses superposition and entanglement or coherence is not going to get very far in that investment conversation. Today's PhDs and technical experts, they are very well versed in quantum and quantum capabilities. And every day we're seeing new breakthrough technologies. So even they are challenged to maintain their currency in terms of quantum computing. The challenge is also, how do they convey the message of quantum to those buyers who are either not aware of the opportunities, not aware of the technology, or they've already got a full portfolio of technology activities? And what about venture capital firms? So there are an increasing number of venture capital firms who are starting to join this space. But if, like some predict, that there's a long time horizon for quantum computing, will they remain or will they start to exit? So one of the challenges that CTOs have is that they have a long list of technology projects. Quantum is often not at the top of that list, even assuming that it's actually on their radar. So how do, whether it's quantum enthusiasts inside a company who can actually understand the opportunities, or people doing business development work on behalf of vendors and researchers, how do they actually move this into the CTO sphere? So they really need to think about those other tactics that I referred to earlier on. As an executive in a bank, I knew that if I had an organization or a leader in an organization in the elevator, I had 20 seconds to identify not the reasons why I wanted them to buy, but the reasons why I wanted them to have a second meeting. And so CTOs are no different. We need to find easy ways to engage them in the quantum conversation. And of course, we need to start learning about it, whether that's books or articles, courses, or media. Some of the organizations that are involved in learning are groups like D-Wave, who do YouTube videos, MIT X Pro, who provides certificates, CERN, who does online, who does YouTube type training, and certainly IBM from their summer program, and QuizKit, and so on. So there is increasing amounts of media over where they were about 3 years ago. So there are lots of new information that's available to you. The question is, how do you consume it? You know, how do you get your understanding of your area or pillar or niche in quantum computing? So one of the reasons why I was excited that the Entrepreneurship Forum Israel asked me to speak today was because this is the perfect time. Now is the time to engage, whether that simply means from starting your plan or actually engaging with vendors and identifying use cases that are relevant to your organization. Armando, I'm going to stop there. I hope this met the expectations, and I certainly enjoyed talking to your group.
Thank you so much, Brian. Next up is dear Minerbi, founder and CEO of Classiq, who will be presenting Preparing for the Next Generation of Quantum Computers.
Sure. Thanks, Armando, and let's go. So I hope you see my screen now. If not, so please tell me. So first, I'm not willing to insult classical computers, right? Classical computers are great, and like for 99.999% of the tasks, they are just sufficient, right? But there are some tasks that even if you took the most powerful supercomputer in the world and give it like, you know, a few thousand years or even billions of years, it wouldn't be enough. And for these kind of tasks, we need quantum computers who can do that, you know, these tasks in few minutes or hours or you know, a bit more, but in a reasonable time. And luckily, almost in any industry, in every large industry, we have several of these important business tasks. So this is kind of the motivation. And I do want to give maybe one example. So I would like to introduce you with ammonia. Ammonia is probably the world's most important fertilizer. And, you know, it's lucky that we know how to produce ammonia, because otherwise we wouldn't have any food to eat. So we do know how to produce ammonia. We do that with the Haber-Bosch process that was invented a century ago. And this is the bright side. The downside is that this is a very energetic consuming process. And actually 2% of the world's energy consumption is dedicated to this process, which is kind of frustrating because, you know, every plant in the world is producing ammonia in room temperature almost with no energy consumption. So if a cucumber can do that, why humanity can't? And the answer is that classical computers are not so good at simulating chemical processes. It's very, you know, computational hard, and it could take, you know, to simulate these chemical processes, it could really take thousands or even more of years. And this is one specific problem that quantum computers excel at. A quantum computer can simulate even large and huge molecules in almost no time, and by that revolutionizing material science, chemistry, and later on drug discovery, and so on. So this is the motivation. And basically, you know, when talking about the quantum computing revolution, so like any other computing revolution, it is about hardware and about software. So let's start with hardware. So the hardware development endeavor is led by tech giants like Google, Intel, IBM, Amazon, Microsoft, and startups. And the beautiful thing is that there are many ways to develop these computers, right? There is no winning technology yet, but fantastic progress is in all methods. We see more qubits, better quality, and we have very good reasons to be optimistic that in the next few years, we'll see the first occasions of quantum advantage, where quantum computers will bring some real business value. And the second part of this revolution is the software and the end users. And indeed, in the last couple of years, we see more and more and more enterprises in various fields. As you can see, this is a very partial list, of course, in, you know, the large financial institutions and automotive companies and chemistry and logistics, aerospace, so on and so forth. And we see more and more of them. And basically, these companies are entering the field, establishing quantum computing software teams. And these teams are trying to prepare the organization to be quantum ready by developing first, you know, locating the use cases, then developing the software, experimenting it on various machines, and, you know, being ready for quantum advantage. So all of these organizations are trying to develop quantum software, and later on we'll see why it's so challenging today and in the future. So a few things that Brian mentioned, but are definitely important enough to mention again. So first, quantum computers are already here, right? This is, you know, in the world, we have already dozens of quantum computers that are accessible via the cloud. If you want, you can, in 10 minutes from now, maybe better 2 hours from now, to design a small quantum circuit, quantum software, and to run it via the cloud free on the IBM machine or on other machines. And these computers can't bring you any value yet because they're in small scale, and we do need more qubits in better quality, and it will happen in the next few years, but definitely you can start experimenting. And of course, it won't replace classical computers. It's just complementary for some specific computational tasks. Great, so now let's discuss the software, how you develop software for quantum computers. So what you see here on the right, so the terminology is a quantum circuit, but basically this is just like saying software for quantum computers. So what we see here, so each of these lines is a qubit, and each of these boxes are quantum gates. Like in the classical world, we have XOR and NAND gates, right? We build the Boolean logic. So these gates are building the quantum logic. This is different logic, different math, but essentially, this is the way to develop software for quantum computers today. And that's a challenge. That's a challenge that because of the quantum software stack is in its infancy and the development is limited to gate level and building block programming. So when you consider how many people in the world can really design useful quantum circuits, quantum software, the answer is very few, right? Many people can do that for toy circuits for 5, 7 qubits. Very few people, maybe a few hundred in the world, can do that for a few dozens qubits. But scaling is practically impossible. Scaling is just too complex design challenge. And this is unfortunate because these are the circuits that will bring advantage. You can't, by definition, bring any advantage with these circuits because they could be simulated on classical computers. So obviously, this is a significant roadblock that should be solved. And this is exactly what we do in Classiq. So before I describe the solution, maybe like one sentence about Classiq. So Classiq was established almost 2 years ago. We are based in Tel Aviv and in the US, raised $48 million so far, like 33 of that will be announced tomorrow. So please don't tell anyone. And we are a product company. We develop a product that is a framework for the development of quantum computing software in a scalable way. So how does that work? So basically, if I need to summarize in one sentence what the Classiq platform does, so Classiq synthesizes gate-level circuits from high-level functional models. And by that, we enable the design of complex quantum circuits. So again, the problem is that the design of quantum software is too complex with existing tools. And this is the problem that we are solving. And basically, when solving this complex design challenge, we took our inspiration from another complex design challenge that was already solved. And this is the classical chip design, right? What you see here, this is an electronic circuit, actually not a very complex one, but yet you wouldn't want to design it at the gate level. And luckily, you don't need to, because in the classical world, you have high-level modeling languages like VHDL, like Verilog, and synthesis tools like Cadence and Synopsys, which basically allow you to define what functionality you want to achieve, but leave the gate-level implementation to automation. And this is essentially what we do in quantum. We allow the quantum software developer to define a high-level functional model of the circuit. It could be in finance, in chemistry, in automotive, in quantum machine learning, anything like that, but only functionality, not implementation. And our synthesis engine, which is the core technology we develop, is generating the gate-level circuit that could, after that, be compiled and run on every quantum computer. And the beautiful thing is that already now it enables users, developers, to design quantum circuits that are just impossible to be designed otherwise. And we and everyone in this ecosystem really look forward to the next generation of machines that will probably be able to bring some business and scientific advantage. Thank you.
Thank you very much there. Next up, we have Dr. Alex Keesling, CEO of QuEra Computing, who will be presenting on useful quantum advantage through co-developing hardware in applications. Welcome, Alex.
Thank you, Armando. It's a pleasure to be here. Let me share my screen and get going. Thank you all for being here. As Armando said, I'm going to be talking about how at QuEra we are working towards developing hardware and applications together to deliver useful quantum advantage to customers. And I think that for people that are not used to being in this world of quantum, there are some things that seem like they are science fiction and they are real. And I think this is a good starting point. What you're seeing here on screen, this is the core of our quantum processor. So we've talked about how businesses should engage with it, how to think about programming these devices, but not about the devices themselves. Here, what you're seeing, each one of these little blobs of purple color, this is a single atom that we have used lasers to trap and control individually. And this gives you a sense of scale for the types of processors that we have built here at QuEra, currently controlling 256 quantum bits. This is small compared to a classical computer, but we're already leading the way in qubit counts for modern quantum technologies. Now, I don't need to elaborate much more on this. I think that previous speakers have done an excellent job paving the way for why quantum computing matters. And in short words, there are just problems that today are impossibly hard to solve. And we use brute force methods that, as we saw, sometimes tend to fail. And when they don't, we are led to live with some suboptimal solutions. And for some of these problems, the thing that connects them, the thing that makes them work, is quantum computing. And quantum computing, in this context and in many others, we talk about as the next generation of computing. But one thing that I would like to emphasize here is that quantum computing is not just the next generation of computing, but the beginning of a much larger ecosystem of quantum technologies that are as hard to predict where they will take us as it would have been to predict the internet in the 1850s, if not harder, because there are a lot of things about quantum technologies that we cannot predict until we build them. That is the nature of the kinds of problems that we are trying to solve. Now, when we talk about what quantum computers will do for us, we're really talking about the potential long-term that they have in what we call the fault tolerance era. And these are the applications that we hear when describing cracking RSA and doing very complex, very large quantum algorithms. However, there's a disconnect between those specific applications and where we are nowadays. So quantum computing will have to go through at least 3 eras during its evolution. Currently, we are entering what we call the NISQ era. NISQ, for reference, stands for Noisy Intermediate Scale Quantum. All of these mean something, but the important thing here is how can we describe the power of the quantum processors that we have available? And in this NISQ era, our quantum processors are already able to do things that cannot be predicted using classical compute resources. And this is huge. It's great news that we are at this point already. However, it's not always clear to see how that extra power leads to useful applications. And in part, it's because these computers are by definition unpredictable, but even in the best case, they are unpredictable because throughout the computation, they incur in errors that are not captured and corrected. For this reason, it is incredibly important, at least during this NISQ era, that we think holistically about the applications, the algorithms, and the hardware itself, because the hardware performance crucially affects the algorithm implementation. Not all hardwares have the same capabilities in terms of the logic that they can perform, and the types of errors that appear are also different. So this is what has motivated us at QuEra to build a full stack quantum computing company that leverages all of our knowledge of the hardware all the way up to the classical and quantum algorithms and matching that to applications. The next step after this NISQ era will be the QEC era, here QEC standing for quantum error correction. And the key characteristics of this will be that our quantum processors will be able to correct for errors during computation, not perfectly, but they will enable us to run larger, more complex tasks on these quantum processors. To get there, from where we are currently in this NISQ era, we will have to develop better quantum controls and to reduce the rate at which we incur in errors during computation. So these are technical challenges that will not be simple, but over the past 10 years, we've seen an incredibly fast advance of quantum technologies using many different qubit platforms. So it is very encouraging to see that the field is moving fast enough that we can really see the QEC era approaching quickly, even though we've only recently entered the NISQ era. And finally, as I said, the FT era, or fault tolerance era, is that in which we can treat a quantum computer the same way that we use our classical computers, where regardless of what hardware we're using, we can write an algorithm. The computer will perform it. It will be limited by whatever memory resources it has available, but we won't necessarily have to think about whether there was an error in the computation or not, because all of these errors will be captured and corrected throughout the computation. But to get there, on top of the technology that needs to be developed to be able to do any kind of basic error correction, we also need to start thinking about what the correct architecture to get us to that scale is. And that is not just the physical platform that is used, unlike classical computers, where we think of the transistor being a single unique thing that defines how the computer works. We are in an age of quantum computing where how we encode physically information varies wildly from one approach to another. And this can be done with using light. In our case, as I will mention, using individual neutral atoms, ions, superconducting qubits, etc. So there is first this layer of understanding which of these physical platforms is best suited to scale, but also how the architecture of the computer itself, given a physical platform, is implemented. And the last step, which I think ties very nicely back to what we heard from Mira a moment ago, is compilation, being able to write algorithms that will be able to run on any hardware without necessarily having to go down to the level of individual qubit gates. But let's get back to this NISQ era. This NISQ era is where we are, and this is what we need to address today to continue moving forward through the QEC era up to the fault-tolerant era. And for that, at this stage, it is that we founded and structured QuEra computing to most efficiently advance through these different stages by working on hardware algorithms and software at the same time. And we are doing this with the intention to, at all times during the evolution of quantum computing, provide the most useful quantum advantage available to our customers. And for this, we are targeting different kinds of applications throughout the different periods of the technology. For our hardware, we are using individual neutral atoms that we manipulate using light. This is technology that was developed at Harvard and MIT over the past almost 10 years. This was the work of my PhD and many others alongside me. And we believe that this hardware is the right path forward because it already allows us to create large quantum systems with 256 qubits nowadays, but we were only at 51 in 2017. This gives you a sense of how fast this field has been accelerating. And they're not only large, but they're scalably large. We can continue to increase the size of the processors. And this word coherent, I must say I'm a physicist, so to me that was important to add there. But this is basically just saying it's not just a bunch of atoms, it's a bunch of atoms that are controllable and that they can be operated as quantum bits without losing their quantum properties. On the algorithm side, our strategy is to identify near-term hardware-efficient algorithms that can be implemented directly on this hardware to leverage the power that this hardware gives us, rather than introducing a large overhead by abstracting things too much at this stage. And the algorithms that we develop are done in coordination with academic and industrial partners to make sure that we're always pushing the boundary on what is not just exciting to our developers, but useful to our customers. And similarly, we're building the software tools that are necessary to continue to integrate the learnings from the algorithms into the hardware and to give tools to customers to be able to do their own development. As I said, QuEra was founded out of work that came out of Harvard and MIT. Among the founders, we have 4 great scientific names, 2 professors from Harvard and 2 from MIT, and we have licensed the IP coming from these universities that is relevant to our work. So this way we can leverage the research that is happening at the university, but this also gives us quite tight connections to be able to pick up on recent developments in the academic world as this field of quantum computing continues to be not entirely industrial, but also very academic. And again, for a sense of scale, the original laboratory at Harvard where the technology started being developed began as an empty room in 2015. By 2017, the Harvard experiment was able to control 51 atoms. In 2019, 2 main things happened for us. The first one is that QuEra was founded to commercialize the technology that we were developing at the university, and this was as a result of seeing how quickly the technology was progressing. At the same time, the university was able to demonstrate basic building blocks for general quantum computing that were of very high fidelity. And just last year at QuEra, we finished the construction of our first instrument with 256 qubits, at the same time as the Harvard team finished their upgrade for a similar platform. And here, what you see here, this GIF of Mario, this is, again, each one of those little pixels, that's an individual atom that is controlled in our QPU. Now, what do I mean when I say that we co-develop hardware and algorithms? What I mean is that we identify the areas where we can get better performance of the hardware if used correctly. And we match that with applications where a quantum advantage might be possible in the near term. For this, there are 3 major categories into which I split things. Usually we talk about industries, pharma, materials, and so on and so forth. But at their core, the thing that sets these problems apart is 1 out of 3. The first one, quantum simulation, which is very much related to the ammonia fixation problem, is to take a system that is hard to solve on a classical computer because its components are quantum mechanical in nature. And rather than trying to take that entire problem into a quantum computer or to continue building on this classical approach that is not scalable, to isolate the problem that is quantum, map that onto a quantum computer as a hardware accelerator and integrate it into this hybrid process that we heard about twice already. Similarly, quantum optimization, applying quantum compute power to try to approximate solutions for problems for which classical computers already give us at best an approximate solution that has no guarantees of being any good. And the last one is scientific discovery. I think it's important to not discount how much work there is still left to be done to understand the potential of quantum computing and other quantum technologies, but also to address scientific challenges for the continued development of the technology. I'll go quickly through some examples of at least the first 2 categories. The first one on quantum simulation, this is actually how the idea, this is a precursor to the idea of quantum computation, to say we have a hard problem, which is trying to simulate nature using classical computers. So why don't we build a quantum system that has enough degrees of control that allows us to faithfully represent what nature is doing? And this is important for problems in material development, where we are looking at a quantum mechanical problem of how electrons interact with one another. Similarly with nuclear matter, nuclear reactions, chemical reactions, such as the nitrogen fixation, and many others. And here, the idea for matching the algorithm and the application to the hardware is to place the qubits in a way that their natural logic, their natural interaction already is encoding the problem to be solved by matching the properties of, for example, a molecule or a piece of matter in the distribution of the qubits. And then the interactions that are happening in this real physical piece of material that we're trying to study are then slowly turned on between the qubits to allow them to implement their quantum logic naturally. This is incredibly powerful, and just as one example, this past year, the Harvard team was able to identify the conditions under which a new state of matter can be created that has been sought after for the past 50 years since its initial prediction, but has never been seen in a material object because the search was not guided enough as what we can now do with these programmable devices. In quantum optimization, a very similar idea is to take a problem that has some kind of constraint that we're trying to solve, such as the design of a new network or traffic routing through it. We also heard about portfolio optimization. All of these things we can write mathematically as graph problems, and that's exactly what we try to do when we use classical computers to solve them. Now, these graph problems we can implement explicitly on the hardware, again, by controlling the chip the chip topology. And because we have individual control over each one of these atoms, we can change this several times a second. So we can address different problems multiple times a second. And here the idea is to use a quantum algorithm that can be broken into a few variational parameters and introduce this into a hybrid loop that allows us to, as we saw before, take classical data, send that to the quantum device, and then extract classical data and close a feedback loop that changes the parameters of the quantum algorithm until we find an optimal solution that is potentially better than what we would find with our classical compute resources only. Now, we have a team here at QuEra of over 30 people working hard on all of these things, but we do it to provide us a service to our customers. And for this, we have built direct partnerships with multiple customers, and we're always looking out to find matching opportunities between applications and the kinds of solutions that we can offer. And we also are going to be connecting to the cloud through the Amazon Bracket service later this year to allow as wide access to this specialized technology as possible. I talked about the beginning of the road of quantum and where we are right now with NISQ and trying to optimize for the resources that we have right now, but this is only the beginning. And given the advancement of the quantum computing technology over the last few years, we have a clear roadmap that can take us to that fault-tolerant universal quantum computer by the end of this decade. And it will take an incredible amount of effort, but this is well within the realm of reason. And we can do this with a single architecture that we are already using without having to think about placing a quantum computer that is the size of an entire building. Thank you for your attention. Here's a picture of our team and my email if anyone has any questions.
Thank you so much, Alex. So as our final speaker, we have AMRITA, both represent the quantum strategy industry, but interestingly, the only person on the panel who actually works in a large corporate environment today. So probably sees it from a different perspective. So AMRITA, would you like to say a few words before we head into our panel?
Yes, sure. And thank you, Armando, for introducing me. And I'm really excited to be here. And thank you so much for inviting me to such a brilliant panel. I think I was looking forward to a lot of information, and I think I have got a lot of information which I was kind of writing when Alex, Neer, and Brian were speaking. So very small introduction about me. My name is AMRITA, working as architect in United Health Group, and also working as head of AI and quantum machine learning as Quantum Strategy Institute. One thing I would really like to share from the consumer perspective. So why I say myself as a consumer, because the organization that I'm working upon, working with, and the industry that I belong is healthcare. And we are not directly producing or doing anything with the making of hardware components or software components in quantum computing. But we surely will utilize all the aspects and applications of quantum computing when it reaches in, let's say next few years to our industry. And how I see it is, so should we wait for some sort of commercial quantum computer being available in the market? And I think from my perspective, I think no, let's start understanding the impact what quantum could bring in all the sort of industry sphere, and especially from the healthcare and life sciences side, I see a lot of impacts that we could have in our industry, especially on the data security side or from the drug discovery side. So yeah, from the application perspective, we see a lot of potential that we could bring in the consumer side of the industry. And the question being how, when, and how we can do that will totally depend upon obviously the transition of hardware. And once we have that system of, let's say, 1 million qubit system quantum computing available to us. But for the time being, we can definitely put all our efforts in understanding, making people aware. And I think creating roadmaps, as Brian was suggesting, that how we can actually inculcate this concept in our industry. So other thing, I would really like to thank EFI for this particular initiative. And I know EFI is doing a lot in organizing different technology webinars. And I think I'm really excited to see more how we can, how we can get more out of this. So thank you for having me here. And I'm really excited to see everyone here, as well as the panelists, as well as the attendees. Thank you so much.
Thank you, AMRITA. So if I could ask the panelists to switch their videos back on, and let's head into the fun part of this, asking some questions. Well, I have some pre-prepared questions, but as I was watching the Q&A come through, you guys came up with better questions than I have. So I'm going to do a mix of both of them. Not surprisingly, the questions on the Q&A are a mix between more, when is this really ready for business, and what are the first business applications that are going to happen, ranging all the way through some very, very specific technical questions. So I'm going to try and mix it up a bit. So why don't we lead off with that first idea? So how close are we to having commercial viability of quantum computers? When do you expect these breakout applications to happen? Quite frankly, I was very surprised that Alex put out there that in 2026, 10,000 qubit machines already commercially available. That's much faster than I was expecting. When does this turn into commercial viability? Ryan, you want to take that one?
Yeah, so I'll start off by just reminding everybody that it was only in 1974 that we came out with the 8080 Intel microprocessor, and it was 22 years later that we came up with the internet. So it's all in your perspective. You know, the suggestion that just 4 or 5 years from now we have that quantum capability, it's remarkable. So it's really important that people don't just look at it and say, today we're at tens of qubits or, you know, hundreds of qubits, and we need a 10,000 stable, 1 million surrounding, you know, those are all things that are going to happen, but we did not wait for the perfect computer in order to use it in a personal or commercial environment. So looking at it from that perspective, it's important that people start to realize, if you go on to the ID Quantique site, for example, a Swiss-based company very actively involved in quantum key distribution and security, they have all sorts of applications that are available today. So I would suggest to people, they don't look at it from a what's going to happen in 5 or 10 years perspective. This will happen incrementally. And the teams like NERS and Alex's are actually going to be creating those solutions and putting them in market quickly. So if you're a consumer, you need to be aware of what's happening and what use cases are relevant to you.
Any other panelists would like to add to that?
Yeah, sure. So the honest answer is I don't know, and probably no one knows currently, right? So I guess that, you know, we need to divide it into 2 eras. The NISQ era, which is the near term, where the algorithms are heuristic, right? So basically, we'll know it if it brings value when we try it. When we'll have 1,000 qubits and we'll try to simulate a complex molecule, we'll know if it works exponentially better than classical computers or not. We have very good reasons to be optimistic, and, you know, we tried in small scale today on small molecules, and we try to scale and extrapolate, but, you know, as it's heuristic, we'll know when we try. Other algorithms are accurate, right? Mathematically proof that they will bring advantage, but this is in the long term, right? We need many qubits, probably error correction, and, you know, all of the Shor's algorithm for breaking encryption and the Grover algorithm for search and so on and so forth. So, you know, most expect it to happen at least 7 years from now. Some are more optimistic, but I guess we'll see. For the near-term algorithms, you know, with 1,000 qubits, so soon we'll have that. So I guess we'll all know, and let's see.
I think there's been a lot of discussion already around the implications of quantum right now in doing molecular modeling kind of work. But how about other areas? Healthcare, business and financial institutions, insurance, logistics. What other application you guys see as near term? Alex?
Yeah, some of this was brought up during the presentations, but for example, in finance, you can think about how to model a portfolio and how to maximize the expected return on your portfolio by managing the risk and decoupling your investment from each other. So these are the kinds of things for which nowadays we have a combination of imperfect solutions with classical computers because the problem is incredibly hard, and people looking at it and saying, I think this is how it should play out. And I don't want to, you know, discount people's intuition. I think that is an incredibly valuable tool. But this is an area where we can expect that if leveraged correctly, quantum parallelism might lead to at least faster processes to approximate these solutions that we just have no way to get an absolutely perfect answer. And these things translate. I mentioned portfolio optimization. These things translate also to things like data analysis, finding elements in a database, and so on. So I think that they are there, but as Nir was saying, some of it at this point is going to be heuristic, because by definition, we cannot know how well the quantum device will perform. And it will be a lot of trying to find what are the properties of these applications that lend themselves to a quantum advantage.
Amrita, I see you have raised your hand. Comments?
Yeah. So talking about healthcare, and since I have some experience working in healthcare, I see a lot of areas, and I'll include some of the areas from life sciences as well. So particularly talking about healthcare, one burning sort of application that I see especially is fraud detection area. So I see in the process in healthcare for fraud detection is like very complex. So once you onboard a customer, onboarding a customer entirely takes like a month or so to just get it in the system for inside a healthcare insurance organization. Now, between these timing, I mean, there are a lot of frauds that happens, and it leads to, I mean, billions of transaction that is just spent in this fraud thing inside a healthcare insurance company. And that is one major flaw. And I think only few organizations, I studied in some papers and all, that they are able to do an automated process of entire fraud detection and onboarding customers, and understanding what flaws and what patterns could initiate or inculcate a flaw in a fraud in a system. So one area I'll definitely look forward to is fraud detection, but obviously I'm not looking in some few years time domain, like 1 year or 2 year time domain. Obviously it's all in the papers and all in the research papers right now, but I haven't seen any practical application being actually built up regarding this. Another one major is product recommendation for healthcare. So healthcare is some sort of complex domain. I mean, it's kind of inculcation of different modules. It is not just consumer platform. You have entire actuary who is kind of designing your pricing system for you, then entire kind of consumer and marketing base who is designing the products for you that needs to be recommended to the end customers and consumer. So this particular thing is very complex, and it would be really interesting to see that the concept of quantum computing, and not just quantum computing, I think the amalgamation of quantum computing plus artificial intelligence can bring something interesting to this area, especially in the healthcare insurance side. I mean, it's really a little bit easy on the consumer side, or let's say, some sort of marketing side to do product recommendation, but relatively difficult in case of healthcare insurance because of this, interaction of different molecules like working in parallel with each other. So yeah, I think two major things I see in healthcare, and obviously like drug discovery and chemical simulation on the life sciences side. These are all important use cases I think we can see from the consumer side or the healthcare and life sciences side. Thank you.
Ryan, additional comments?
Yeah, just round out this conversation. JP Morgan Chase, Goldman Sachs, they're all making large investments in quantum for modeling. Generally speaking, around, as Alex talked about, portfolio optimization. And insurance companies increasingly are getting involved because there's so many different use cases, whether you're talking about claims, recommendation, marketing, fraud, as AMRITA mentioned. So increasing numbers of those financial services organizations who are making investments.
Maybe one more point, Armando. I think that the common ground for all of the companies and industries that are now involved in quantum is not a use case or a capability. Is that there are, companies that are in the frontier tech. They want to be there. They understand that a huge paradigm shift is going on, and every large company will find fantastic use cases that could be revolutionized by quantum computers. So I think this is the common ground. And indeed, you see financial institutions at the front, and automotive companies and aerospace and so on and so forth. But the common ground is technology, not the use case.
Oh, just to add to that comment, I am old enough, as you can tell by my bald head, that I've seen the classical computer industry really develop from its origins. And I think the right answer here is it's impossible to predict, because you never know what algorithm is going to wind up in market first and is going to catch fire. In the same way that no one in a million years would have predicted that VisiCalc was the game changer application that allowed the PC industry to happen, right? Who would have ever made that prediction, right? So I do think it's early enough that it is unpredictable. However, it is going to happen exactly the way that the panelists here have described, which is you have lots of smart people all acting in parallel, using the tools being created by lots of other smart people. And some set of those algorithms will wind up being kind of the application that drives the industry, that drives software and hardware purchases in volume. So that was all a long-winded way to come back around to one of the questions asked by one of the attendees, which is, I'm going to paraphrase here, but I kind of got the meaning out of the way it was phrased. If this stuff is so far in the future, why are tens of millions of dollars being dumped into this thing from investors already? Why can't that money be put to use in other places that are going to yield more near-term results? Or near-term returns? How's that for a way to phrase it? So again, paraphrasing someone as an attendee. Who wants to take that one?
Well, I'll start off if that's okay, Armando.
Go for it.
Maybe you'd like to take this one. So really the question is based in, are we waiting for a universal fault tolerant computer, the perfect computer, or perfect quantum computer to say it's been worthwhile making the investment? And that's really the wrong question to be asking. We need to be looking at it from an iterative perspective, incremental benefits over the years, and seeing where companies can actually get those benefits out of it. Today, there's a Samsung Galaxy Watch that has a quantum random number generator chip already inside it. So quantum, in a sense, is already in market. Samsung did not wait 10 years until a perfect universal fault tolerant computer. So there is an incremental benefit over time as more qubits, more algorithm capability, and that certainly behooves organizations to start thinking about how they're going to incorporate.
Anyone want to add to that? Okay, so let's go. I'm going to do another attendee's question here. The cracking of factoring encryption by quantum has been discussed for quite a while because of developed algorithms that are quantum implementable. I'm sure this is a reference to Shor's algorithm. And while there are a set of hugely important implications of that capability, what are the other actual deployable algorithms that are well-defined, and what class of problems can they address? So specific algorithmic approaches that are enabled beyond markets, now talking about specific algorithms that are enabled by quantum computing that are distinct from classical computing. And while we're at it, we might as well also deal with the when is the Bitcoin encryption cracked? Alex, you want to take that?
Not the latter, but I can talk to the former.
The latter is the more interesting one.
I agree, and we've talked about it before. But I mean, it's basically just asking, when are we going to have fault-tolerant quantum computing? I believe by the end of the decade. But either way, yeah. So I think historical perspective is important here. One is yes. What is known as Shor's algorithm has been discussed for a long time. This is what would lead to being able to crack RSA encoding. It kind of was the spark that made the quantum computing world catch on fire, because there's a very beautiful mathematical demonstration that using the mathematical tools that describe quantum mechanics, one could solve this problem of effectively finding prime factors. This is what made people realize that quantum computers, as far out in the future as they may be, could be incredibly powerful for something very specific that we care about, because this problem is tied to security, to how we communicate. There are other algorithms that have been developed since that mathematically one can demonstrate there is a speed up relative to any best known or even possible classical algorithms. One example of this is the Grover algorithm that allows to search an unstructured database faster. But there are very few specific algorithms for which we have this level of knowledge. And it's very hard from first principles to be able to develop quantum algorithms in the absence of any hardware to support it. But it's also very hard to prove a lot of these things. And I mean, even nowadays, when we talk about encryption, from a mathematical point of view, we think that it's hard, but there's no proof, right? So this is something that is very complicated when talking about these topics about what's easy and what's hard, is that there's a lot that is not known, even for things that we do on an everyday basis.
Anyone want to add to that? Okay, so something I did see a lot in the chats was either questions regarding, all right, so how do I develop expertise in quantum computing? How do I get a certificate in quantum computing? And all of them are kind of around the general topic of, okay, I'm a software engineer. How do I become a quantum engineer? What resources are out there? Who wants to take that one? AMRITA.
Okay, so this is one of my favorite sort of topic. I am a software engineer, and I do not have any formal education on quantum computing. I'm not a postgraduate or not a PhD in quantum computing. But the very first thing that sparked me into this domain was just out of passion and a very strong interest in understanding physics. Obviously, I did not understand all the maths and other stuff. But the very first thing is, you want to do this. Like, the passion is very important, and you have the right expectation towards it. You have made it in your goal. Now, second thing is quantum computing is not very easy. Like, it's not very easy to design an algorithm, right? There are very few algorithms that are present that that can give you some maybe value out of it, or there are very few applications that has been actually being designed till now, and it's still in in the process of few years. Now there are many documents that are online that are present. I can share with you in the chat. Plus there are several books that I kind of referred. One was Michael Nelson's and Isaac Chung, Quantum Information and Quantum Computation. So that I find it very useful. I mean, in the first when I read it, I wasn't able to understand, okay, what's going on in here. Like, it's very difficult to, shift the mindset of classical paradigm to a quantum paradigm, because in classical world, you just think in binary, like 1 and 0. But now here you have like all those superposition things, going on, and a lot of possibility with just one encoding. So it's very difficult to first shift the mindset. And so once you start maybe reading the book, please do not, get afraid that, okay, I'm not understanding anything, read twice or maybe read thrice if you're actually, into it. So very first thing is get all those books, there, a lot of IBM Qiskit stuff is out there. And it's like everything is in very simple language. You'll be able to understand it. And if you do not, please, go ahead and, reread and read and stuff. So I'll send out to you in chat some of the materials that I kind of, did, learned. And other things that are also very important. I think Brian is also raising his hand. So I think he wants to add more to it. But yeah, I mean, there is no shortcut way to switch from software engineering to quantum engineering. You need to actually learn very hard. And the very the good and the surprisingly good thing is now people are not actually looking for PhDs everywhere. They're also looking for normal software engineers who can do coding in Python, and they need not to go into entirely the intricacies of quantum physics and stuff. So I think good news if you are like very good in programming and all. A lot of organizations are looking for those people. So yeah, Brian, I can, move it to you.
So I'll just add to that. My personal journey was through TU Delft in the Netherlands, and CERN, who was also involved with quantum computing education. But I augment that with, YouTube videos from D-Wave and various other organizations. I think some people have put some ideas already in the chat. The interesting thing is today in 2022, there are so many more resources than there were just a few years ago. I recently did a post around quantum education, and there are at least 20 master's programs around the world that are dedicated. So not PhD, but at a master's level. So there's an increasing amount of educational opportunities.
Thank you, Brian. So we've kind of touched on the periphery of this specific question coming from the audience, but what is quantum computing's relevance for machine learning and natural language processing, AI in general? Who would like to take that one? No one wants to take that one?
Yeah, so this area is accelerating pretty fast in regards to research, in enterprise, in some of the hardware providers. Nothing is quite proved yet. It's essentially about more heuristics, and there are some good reasons to believe that quantum computers could accelerate some aspects of machine learning. Maybe you'll be able to train the networks, with less data or noisier data. And when, looking ahead, so the HHL algorithm is, solving exponentially faster specifically set of linear equations, which is obviously very relevant for machine learning. So I guess there are opportunities in the near term and also in the long term, but mainly this is quite new and a lot of research is being done these days. So a lot of potential, and we'll see where it goes very soon.
Okay, I'm going to take one more kind of more contrarian question. So we're actually two more contrarian questions. First one is, we're clearly reaching the end of Moore's law. We're down to the point where a transistor on a chip is handfuls of atoms. It's just not going to get any more dense than that. We're at the extreme limits of what Moore's law has given us for the last number of decades. Does this get replaced by a quantum computing accelerated technology adoptive curves? What about Nevin's law? Alex, would you like to take that one?
Yeah. First, interestingly, about Moore's law, it seems like it's still continuing, even though the size of transistors has not changed by that much. For context, Moore's law was based on saying that the number of transistors that we could pack within a given area was doubling about every year and a half. Nowadays, we still see advances in computational power that are coming from how specifically we process that information, even given a set of resources. Plus the fact that we have specialized accelerators now with GPUs and so on. So I think we still have a little bit of time to give Moore's law before we declare it dead. But this idea of how does computational power increase as a function of time, and saying it's exponential, every 18 months it doubles or so. This is something that we're starting to see in the quantum world as well. And this was attributed to Hartmut Neven, called the Neven's law, that says that we're seeing effectively the same kind of effect, that quantum processors are doubling in size at a constant rate. So the quantum computational power is growing exponentially. And for certain problems, we know that quantum computers should be exponentially faster than quantum computers for a given set of resources. So there's a double exponential increase in computational power that is coming from quantum processors nowadays. So things are moving very, very quickly. And I think this ties back to all of these questions about where are we going to be in 4 or 7 years? Well, exponential growth is something that is hard for our minds to wrap around sometimes. Niven's law tells us that quantum computing is enabling new possibilities at a doubly exponential rate.
Anyone want to add to that? So let me go on to my second controversial question as the final question for this. So lots of people have talked about the singularity, the technological singularity event, you know, highly publicized by Ray Kurzweil, by Dr. Peter Diamandis, who happens to be a fraternity brother of mine and Alex's as well. So there are a lot of people in the classical computing community that feel that classical computers have all the enabling technologies that they need to achieve AGI, artificial general intelligence, at an equal level to human intelligence. And as soon as that singularity event happens, then all bets are off. At that point, we have exponential growth happening through classical computing, obviating the need for quantum computers, because classical computers will fulfill that long-term role as a result of hitting the singularity event. Comments about this? Is it even possible to achieve a singularity event through classical computing? AMRITA?
Yeah, so I was reading through this, so the concept of artificial general intelligence or singularity. So in a very, very simple terms, it's something like mimicking the human itself. And I'm not exactly sure that it's going to happen, perhaps maybe end of the decade, because it's not something, I mean, so intelligence is not something that's one dimensional, it's multi-dimensional sort of, term. And mimicking the behavior of human, applying all the cognitives that human can apply in a machine, it's like real difficult. But another thing I could think about is, so the classical computing, that how it works in, for example, take an example of one human architecture. You have your input, you have your CPU memory unit interacting to each other, and then your output. Now, even your CPU and memory unit interacting to each other, that does not exactly happen how a human brain works, because in order to mimic the behavior of human, you need to mimic how the brain works, right? So it's not, it's a very complex thing. I mean, right now, how the classical computing is working, it's like very difficult to mimic the human brain. However, they're like memoristas and all, they are kind of mimicking the neurons and, how our human brain is working. So it could require like maybe billions of memoristas to be, to be built in order to exactly mimic maybe how a human brain works. But I cannot think it, it is going to happen maybe till the end of the decade. But yeah, I mean, others can join in. That's just my view of how I see this AGI thing working, or, if we are able to reach a singularity point. So yeah.
Alex, you want to add to that?
Yeah, I want to actually dissect your question a little bit. First, you asked, do you think that classical computers can reach to singularity? And from my point of view, if I just abstract myself from this entire thing, basically what we're talking about is, can we simulate the human brain? And from an information, theory perspective, I think that classical resources should be able to do that. Basically, you're asking, at some level, you're asking, is the human brain a classical computing structure? And I think it is. The alternative is that you need quantum computing because the brain is quantum. And that is, I guess, very speculative. So can we, in principle, have a classical system that reaches human intelligence? I think the answer is potentially yes, but whether we will be able to design the correct architecture to support it, that is a very different question, right? And that's a question about us, not about the capabilities of quantum computing. So that's kind of the first part of your question. The other part that I thought was interesting that you raised is, would that then make quantum computing not necessary? Because it means that classical computing has advanced so much. And I think the answer there is clearly not. Because we have definite proofs that there are things that a classical computer, no matter how smart it is, will never be able to do that a quantum computer can. So maybe a next interesting point is there a quantum analog of the singularity event? And that I really have no idea. But yeah, is singularity possible classically? From a completely abstracted point of view, I believe the answer is yes. From a practical point of view, who knows? Would that make quantum computing useless? Absolutely not.
Thank you, Alex. I love that answer. We've now reached the end of our session today. I wanted to thank all the attendees, all the panelists. This was a great session. I very much enjoyed it. Thank you to everyone. Brian, since you were the keynote here, would you like to do a final word? You're muted.
I'd like to thank the Entrepreneurship Forum for being so entrepreneurial and pioneering in its thought process. I look at your agenda for the next number of meetings, of course, starting with quantum computing, and I'm thrilled. I'm really looking forward to seeing what else you're going to be delivering in the future, and thanks very much for having us.
Well, thank you. Thank you to everyone. Have a good rest of the morning, evening, middle of the night. Thank you all. Bye-bye.